What if I told you that everything, and I mean everything, from the farthest star to the phone in your hand, is made of tiny vibrating strings of energy? I know, it sounds like something straight out of science fiction, right? But it's actually the core idea of one of the most ambitious and, frankly, mind-bending theories in all of physics. We're talking about the search for a single, elegant description of reality itself. So today, using Stephen S. Gubser's The Little Book of String Theory as our guide, we're going to dive right in. For more than a century, physicists have been on this epic quest, almost like cosmic detectives, trying to answer this one huge question. We've gone deeper and deeper into the heart of matter, from molecules to atoms and then to quarks, only to find out that the very foundation of reality is a giant puzzle. And that puzzle really begins with a massive conflict right at the heart of modern science. So, the story of 20th century physics is really the story of two incredible, world-changing theories. They are both fantastically successful at describing their own little corners of the universe. The only problem? They can't both be completely right, at least not when you try to use them together. Okay, so on one side, you've got general relativity. That's Einstein's masterpiece, right? It describes the beautiful, graceful dance of planets and galaxies. Then, on the other side, you have quantum mechanics, the super bizarre but stunningly accurate rulebook for the tiny, subatomic world. And they each work perfectly in their own domain. But, and this is the big but, when you try to use them together, like to describe what's happening inside a black hole where you have immense gravity crushed into a tiny space, their equations just break. They spit out impossible answers, like infinity. It's like the universe has two completely different instruction manuals that just flat out contradict each other. This is where string theory makes its grand entrance. See, it doesn't just try to patch one theory onto the other. No, it proposes something totally new, a completely different foundation for reality. It's an idea that is, at the same time, elegantly simple and just profoundly strange. So here it is, the revolutionary idea. What we've always thought of as fundamental particles, electrons, photons, quarks, they aren't little dots. String theory says they're all just different notes being played by a single, unimaginably small, vibrating string of energy. And Gubser puts it perfectly here. Everything, from the light hitting your screen right now to the atoms that make up your body, is at its most fundamental level made of these little energetic strings. That is a radical shift in how we see the world. And this is just such a great way to think about it. Picture a violin string. You can pluck it, you can bow it, and by vibrating it in different ways, you can create a whole range of musical notes. Well, string theory says the universe works pretty much the same way. A string vibrating in one pattern, that looks like an electron to us. A different vibration, that's a photon. Another one, a quark. All the incredible diversity of particles we see is just a cosmic symphony being played on these fundamental strings. And this is why that shift from a point to a string is such a huge deal. When physicists tried to combine gravity and quantum mechanics using point particles, the math, as we said, just fell apart. The equations gave them infinities, which is basically math's way of screaming, this makes absolutely no sense. The theory was just unworkable. But strings? Oh, they change everything. Because they actually have a little bit of length, they don't collide at a single, infinitely tiny point. Their interactions get smeared out, which makes them much gentler. And it completely avoids those nasty infinities that plagued the old theory. And just like that, gravity and quantum mechanics can finally play nicely together in one beautiful mathematical framework. So, problem solved, right? We're done? Well, not so fast. This incredibly elegant solution comes with a price. And that price is a universe that is far, far stranger than we ever could have imagined. To make the math work, string theory makes some predictions that are, well, they're truly bizarre. One of the first big problems was this thing called the tachyon. The early theory predicted a particle that had negative mass squared, which is just a huge mathematical red flag. It doesn't mean something's lighter than nothing. It's a sign that the whole theory was built on a really shaky foundation, kind of like a pencil balanced on its tip, just ready to topple over. So to fix this instability and some other nagging problems, the theory made a shocking demand. It required our universe to have not 3 spatial dimensions or even 4 space-time dimensions, but this many, 26. So you might be asking, okay, why 26? Where on earth did that number come from? Well, it's kind of like a cosmic balancing act.
The theory had this negative instability problem from quantum effects, but it also had a positive effect from the way the string vibrates. And it turns out that in exactly 26 dimensions and only 26, those two effects perfectly cancel each other out, which creates a stable, consistent theory. The math just wouldn't work any other way.
Thankfully, a kind of upgraded version of the theory came to the rescue. By introducing a new idea called supersymmetry, this new superstring theory got rid of the tachyon problem completely. And as a really nice bonus, it brought that dimensional requirement down from a wild 26 to a slightly more manageable, but still pretty baffling 10. That's 9 dimensions of space and 1 of time.
But just when physicists thought they were finally getting a handle on these 10-dimensional vibrating strings, yep, the theory had another surprise up its sleeve. It turned out that strings weren't the only things in this cosmic play.
You see, the theory has been evolving in these dramatic leaps. After the first big revolution in the mid-80s proved superstrings were a serious contender, a second revolution hit in the 90s, and that one revealed that the theory was much, much richer than anyone thought, containing not just strings, but all sorts of other objects, too. And these new objects are called branes. It's short for membranes. You can have a 2-brane, which is like a sheet. A 3-brane would be a 3-dimensional volume. The theory basically says you can have branes of all sorts of different dimensions, all coexisting with the strings in that 10-dimensional space. And this is where it gets even more interesting. It turns out that strings can be open-ended, with their ends actually attached to these branes. You can almost picture it like a cosmic piano, with the strings stretched between the branes, able to vibrate and create the music of the universe. This just adds a whole new layer of complexity and possibility to the entire theory. Okay, so let's take a step back. We have vibrating strings, we have extra dimensions, we have these branes, and it all forms this incredibly beautiful and coherent mathematical picture. But this leads us to the ultimate question, the billion-dollar question. Does any of this actually describe our universe? Is it real? And this right here is the central tension of string theory today. It's a theory with so much promise, one that seems to whisper the deepest secrets of the cosmos. And yet, for all of its mathematical beauty, it is yet to make a single, testable prediction that we've been able to confirm with an experiment. But don't think for a second that people aren't looking. The hunt for evidence is absolutely on. At massive experiments like the Large Hadron Collider, scientists are smashing particles together at insane speeds, hoping to catch just a glimpse of something new. They're looking for signs of supersymmetry, which is a key prediction of the theory. They're studying the most extreme forms of matter you can imagine, searching for clues that might point to hidden dimensions. It's a long shot, for sure, but the hope is that buried in the debris of these collisions, we might finally find the first notes of that cosmic symphony string theory predicts. And that's where we're left, standing right at the edge of our own understanding. Is string theory the ultimate blueprint for reality, a true theory of everything? Or is it just a magnificent mathematical castle in the sky with no real connection to the world we actually live in? The answer, whatever it is, would change everything we know about our place in the cosmos. But for now, it remains one of the greatest mysteries in all of science.